in the last class we saw that whenever we make a measurement, we always take a sample of some quantity, and then we obtain the mean of that sample. We get the sample mean and the sample standard deviation, and from there we are trying to estimate the character of the population mean and the population standard deviation. So, we have a smaller number of data and we are somehow trying to assess the character of the quantity out there. And in doing so, we have seen that we had reversed the argument. For example, if we have the measured quantity of x bar, which is the average from the sample, and the standard deviation obtained from the sample. So, these are measured. And we are trying to find out, the population mean and the population standard deviation. So, this is the target. And then the central limit theorem stated that if the number of data points is sufficiently large, then the means will be distributed as a normal distribution, something like this. And the mean of that normal distribution will be the population mean mu, and the standard deviation will be the population standard deviation divided by the square root of the number of data points taken. So, that is the claim of the central limit theorem. Now, what we had done in the last class in an example that we worked out, in that we were given these and we were trying to figure out if we have a particular value, suppose this is the x scale and here is my x bar. We are trying to figure out if I can define a range around x bar and can claim that the actual mu will lie somewhere in this range. And in doing so, we argued that if say mu is here suppose, then the distance from x to the mu is the same as the distance from the mu to the x, and therefore, the probability that mu lies within. Now, here we had written it in the form of a multiplier times the standard deviation within z of z is the multiplier of x bar. And then we said that this is the same as P is equal to x bar lies within the z of mu, sorry. And this z is a factor times the factor is z. So, that is a factor and this is the multiplier of the standard deviation. So, standard deviation. Now, if we express it this way, then it is possible to obtain it, because the value of z, or for each value of z, each value of z, for example, if the z is here, the area under the curve to the left of z can be found from the z table, and from there we can solve the problem. So, the z value is a factor, there is a multiplier of the standard deviation, something times the standard deviation. So, x bar, then x bar, say x bar is lying z of mu. So, if x bar is at a distance z from mu, then it is possible to find out what is the area under the curve to the left of that value of z. And from that we were able to calculate the probabilities, and hence the confidence with which we can state that mu will lie within a certain range of x bar. Now, notice one thing, what is the standard deviation here? It is the standard deviation of the distribution of the means, which is this, and in that we do not know sigma, because that is a target, that is something that we do not know, that is of the population out there. So, we argued that in the absence of the value of sigma, we estimate it by the measured value of the standard deviation, which is s. So, we argued that we will use s as an estimator of sigma. You might ask, how logical will that be? Won't that incur errors in the calculation, in the measurement? Yes, it will. But there is a logic behind this substitution. The logic is that if the number of samples is reasonably large, then we have seen that the central limit theorem claims that the distribution of the means will be almost a normal distribution. And if you increase the number of samples even more, it will not improve the approximation any further. So, we know that around 25 is a good number of readings to take. Now, if we take that minimum number of readings, then the theory in statistics, which I will not get into the details of that, I will not get into, shows that if the number of samples is reasonably large, then the difference between s and sigma will be really small. And since the actual value is sigma divided by square root of n, and n will be a reasonably large number, square root of that, therefore, the difference of sigma by square root of n and s by square root of n will not be significant. That is why this justifies this use of the s as an estimator of sigma. But one thing is clear, that we cannot do anything otherwise. We do not have a handle on sigma, we only have s, and therefore, we have to use s as a estimator of sigma. So, we have we will then substitute in place of sigma by s, which is known, n known, and therefore, we have a handle on the standard deviation of this curve. If we know that, then what factor needs to be multiplied with the standard deviation to get the value, that is also known, and therefore, we can then refer to the z table to extract the value of the probability. Now, we know, we have seen earlier that that if now I will plot that as a number here, and here is my, I give a range. This is the value that I have measured, which is x bar, and suppose here is x bar minus the standard error of the mean, and this is x bar plus the standard error of the mean. Then I know that in the curve that we had already drawn, here I have this normal curve, and we are talking about a range which is, this is my x bar and this is the this value is here and this value is here. So, it is basically within one standard deviation, and we know that the area under this curve here is 68.3% of the whole. What does that imply? It implies that if I define a range which is x bar minus the standard error means the standard deviation divided by square root n, and x bar plus the standard error. If this range is defined, then I can be certain that the actual mean will lie within this range, and I can state that with a confidence of 68.3%. So, this is important. It is important to understand what is the actual meaning of this statement, and this in many cases is written as the error bar. So, we will see graphs something like this. So, these are the data points, and if you add the error bars, these will look like you normally put the extremities like this. So, this is how the graphs are actually drawn. This means here is suppose a parameter or an independent variable, I would rather say. Variable, and here is a dependent variable. Now, for each independent variable, you measure the dependent variable and you may get these values, okay? But you will also specify by an error bar. And what does that error bar signify? It signifies that you are 68.3% confident that the actual value of the dependent variable for that independent variable will lie within this range. So, with 68% confidence you will state that. That is the meaning of the error bar. Now, you might say that the 68.3% is not a very large extent of confidence. Yes, surely we will have to deal with that. We would see how to represent a higher level of confidence, but in general the meaning of the error bar is that. So, whenever you read an error bar, you see an error bar in a paper, you have to interpret that accordingly. It does not mean that the actual value will be in this range. actual value can be as well be outside, because this confidence level is not very large. That means essentially you are stating that there is 68% probability that the actual value, the actual value that we are trying to measure, which is out there, will lie somewhere in this range. Okay. Sometimes we state the value. For example, suppose we have measured something and we have got x equal to say 3.56 centimeters, but then we will have to state it with an error which is plus minus say 0.03 centimeters. So, we always state it like that, because we can never state the value exactly, because we know that it is subject to some random errors. Okay. Sometimes these are also expressed a little bit differently as a percentage error. So, that can also be expressed as a percentage error, something like this. I will write x as the average value that you have measured. This is in centimeters maybe, and then plus minus. Now, you have to put the standard error, which is a standard error. I can write that delta x, the change in x divided by your x bar, which is the extent of error in fraction into 100, this many percentage. This is the percentage error calculation. Okay. So, you might state the result in both these ways. This is in absolute value and this is as a percentage error. So, the point that I am making is that whenever you make an observation, a measurement, you state the result of the measurement always this way, and the extent of this error that you state is also objectively calculated. Let me just illustrate that by means of an example, and then I hope that will be clearer. Suppose you have made a measurement of two variables x and y, and you have made a large number of data points, say n equal to 25 data points you have calculated, and then from there you have found by calculating that x bar is 5.018 and y bar is 3.335. Okay. But the data that you have calculated, this 25 data points for x, 25 data points for y, from there you can also calculate the s of the x variable. S is the standard deviation of the x variable, and suppose you know how to do that. I have already said how to do that. You found that to be 0.16, and the s of y is say 0.21. Then how do I specify these values? We need to calculate the standard error. So, standard error in x will be sigma by square root of n. Now, sigma we do not know, but we know the s, therefore, we substitute by that. So, 0.160 divided by square root of n is 5 is equal to 0.032, and the standard error in y is this sigma, this would be x and this would be y, by root over n, and we again substitute that by the standard deviation in y, measure standard deviation in y. So, 0.211 by again 5, because the number of data points were the same, and then this comes to be 0.042. And therefore, having done this calculation, we will state that I have measured x as here 5.018 plus minus this 0.032, and I have measured y as this 3.335 plus minus 0.042. Notice one thing, that after having these values that you have actually measured, when you calculate the mean, you could have calculated up to a larger number of decimal points. Similarly, for the standard deviation, you could have calculated to a large number of decimal points. If you have a calculator with 8 digits, you can do that. But it will make no sense, because the measurement has been taken with some kind of apparatus which has a least count, and it makes no sense to specify something to a least count that is below that least count. So, if the measuring apparatus has an accuracy which is meaningful to the third decimal place, you should specify everything only up to third decimal place. There is no point going beyond that. That is why in this case I have expressed everything up to the third decimal place. But remember, to what decimal place you will specify it, there is no pre-assigned prescription for that. You have to do that depending on the instrument that you use, depending on the accuracy of that instrument. Okay. Notice that everything hinges on the idea that in the distribution of the means, the standard error of the mean or the standard deviation of this graph is sigma by square root of n. And I have already told you that in the normal distribution curve, you can easily integrate the normal distribution curve and find out how much area is contained within some specific ranges, specific limits. And if it is up to the standard deviation of this graph, then it is 68, the area under the curve. So, area within mu plus standard, sorry, mu minus to mu plus standard error, mu plus standard error, this range is 68.3%. And we have also seen that the area, if you can calculate this, then you can also calculate how much does it have to be taken, so that the area under the curve is 95%, and that has been calculated. Area within, I want to have this at 95%, mu minus, it is 1.96 standard error, and mu plus 1.96 standard error. This range is actually 95%. And the area within, sorry, mu minus, if you want to have 99%, then 2.58 SE and mu plus 2.58 standard error. So, if you consider a larger range, which is 1.96 standard error, this is standard error. then the area that is contained, this area that is contained, which is this area, I'll hatch it. This area is 95%. This has great import. In some fields, the confidence level of 68.3% is considered too low, and there the demand is that you have to state it with a confidence level of 95%. And if that is so, your error bar will have this is the mean value that you have calculated, and this is x bar plus 1.96 standard error, and this is x bar minus 1.96 standard error. In that case, you have to specify that way, and this is actually true for most fields. So, but there are some fields that demand even more level of confidence when you state the result, for example 99%. In that case, you have to put 2.58 here. And there are some fields, especially something like, for example, the discovery of a new particle in particle physics. The discovery of gravitational wave is a discovery. In case of the discoveries, the demand is far larger. The demand is something that is stated as 5 sigma. What does 5 sigma mean? So, in discoveries, when we will say something has been discovered, in discoveries, the demand is 5 sigma. What is the 5 sigma? It is this number. This number will then become 5. That means almost the whole area is enclosed within 5 sigma, 5 times the standard error of the mean. And practically the whole area is enclosed. What does this physically mean? It physically means, I will just write it, it physically means that 5 sigma will mean, I will put the line here, yeah. This means that only 1 in 3.5 million data points can lie outside this range. Which means that if the result that has been obtained, for example, the discovery of Higgs boson was an observation where there was a kink in a graph. Now, if that kink happened due to random chance event, then the possibility of such a random event being detected is 1 in 3.5 million. Only when we reach that level of confidence, we say that we have made a discovery. So, it is very, very exacting demand for the scientific community. They have to make measurements and repeat it a large number of times, and then only one can reach that kind of 5 sigma level of confidence. That means, if the observation that has been observed is caused by a something that is not what is intended to be, then the probability of that happening is only 1 in 3.5 million. That means the area under the curve within 5 sigma is absolutely there. The amount that is remaining is only this much. So, that is the kind of demand in case of discoveries.